Raman spectroscopy exploits the scattering of light to gather molecular information unique to the material under investigation. When light strikes a molecule, most of the energy is not absorbed, but scatters at the same energy as the incident light. However, a small fraction of scattered radiation appears at energies differing from the incident radiation. These shifts in energy correspond to vibrational states of molecules and can be used to identify, quantify, and examine the molecular composition of the sample under analysis. This video will introduce the theory behind this technique, demonstrate a procedure to perform the technique in the laboratory, and present some of the ways in which this method is being applied in industries today. The interaction of radiation with the sample can be thought of as collisions between photons and molecules. An incoming photon excites the molecule to a short-lived virtual excited state, from which it will quickly decay back to its ground state and emit a scattered photon. When there's no exchange in energy taking place, a scattered photon has the same wavelength as the incident photon, and this is called elastic Rayleigh scattering. In a small number of cases, there will be inelastic interactions between the photons and molecule, causing excitation or relaxation. If the molecule is raised from a ground state to a virtual excited state and drops back to a higher energy vibrational state, then it has gained energy from the photon. This is also called Stokes scattering. If a molecule in a higher vibrational energy gains energy and drops back down to a lower ground state, then the molecule has lost energy to the photon, giving rise to anti-Stokes scattering. At room temperature, the number of molecules in the ground state is higher than those in a higher energy state, causing Stokes scattering to be more intense and more commonly examined than anti-Stokes scattering. Molecular vibrations and rotations arising from these interactions with incident photons include symmetrical and asymmetrical stretching, scissoring, rocking, wagging, and twisting. These molecular vibrations are used not only in Raman spectroscopy, but also alongside it with other techniques, like infrared spectroscopy. A vibration is Raman active, or detectable by Raman spectroscopy, when it causes a change in the polarizability, or the amount of distortion of its electron cloud. A vibration is infrared active when it induces a change in its dipole moment. For example, symmetrical stretches, like expansion in carbon dioxide, cause electrons to move away from nuclei and become easily polarizable, but do not change the dipole moment. An asymmetrical stretch, on the other hand, results in change in dipole moment, but no change in polarizability. For these reasons, Raman and infrared spectroscopy are treated as complementary methods of chemical analysis. Raman spectroscopy is performed by shining an intense monochromatic laser on a sample. Radiation emitted from the sample is collected and the laser wavelength is filtered out. Scattered light is sent through a monochromator to a CCD detector. The Raman spectrum of a sample is a plot of intensity of scattered radiation as a function of shift in wave numbers from that of incident radiation. Peak shapes and intensities can indicate molecular structure, symmetry, crystal quality, and concentration of material. Now that you understand the theory behind this method, let's explore a protocol to perform Raman microspectroscopy on a sample. To begin the procedure, turn on the required laser and select the correct optics for the wavelength used. Give the laser 15 minutes to warm up before beginning the experiment. In the meantime, turn on the computer and load the instrument software. Choose the correct wavelength for the laser used. Perform the required calibration of the Raman spectroscope. This can be done using a silicon wafer placed on the microscope stage, but here an internal silicon reference sample is used. The Raman spectrum is obtained using an appropriate exposure energy and time. The silicon should give a strong peak around 520 wave numbers. Once calibrated, place the sample underneath the microscope and focus on the layer of interest. A dark enclosure is used to remove stray light. Make sure the path of the laser is not obstructed by light-absorbing or Raman-active layers so as to obtain a clean spectrum. Select the range of wave numbers that should be scanned by the monochromator. Select a laser intensity that produces sufficient signal but doesn't damage the material under investigation. This can be checked by imaging the same spot twice. If the spectrum changes, damage may have occurred. If the sample is in a completely dark enclosure, a background scan is not needed. Acquire the spectrum of the sample. Investigate the data using appropriate software and by comparing with available literature. Cosmic rays appear as sharp and intense peaks that must be removed. Laser interference with certain substrates or contaminants can result in a baseline, which is removed by fitting an appropriate curve to the regions of the spectrum that are not expected to contain Raman peaks originating from the sample. For some materials, the different Raman peaks overlap to a degree that peak deconvolution might be necessary. After these steps are completed, resulting spectra will represent qualitative and quantitative data on species present in the sample. Here, we'll examine the Raman spectrum of carbon nanotubes, which are very small, hollow, single or multi-layered rolls of graphene sheets. The Raman spectrum taken from multi-walled carbon nanotubes using a 514 nanometer laser is shown here. The G-mode peak at 1582 wave numbers is related to the sp2 hybridized carbon-carbon bond that can be found in any graphitic material. There is also a prominent D peak at 1350 wave numbers, representing scattering caused by a disorder in the crystal lattice. The ratio of the intensity of the G and D modes quantifies the structural quality of the nanotube. Developments in lasers and computer technologies have made the once tedious Raman spectroscopy one of the most widely used techniques for chemical analysis. Solid oxide fuel cells, or SOFCs, have the potential to become a major source of low-emissions energy in the coming decades. These cells work by electrochemically converting the energy of a fuel and an oxidant, in this case solid oxides, to electricity. There is still some difficulty in characterizing the electrochemical mechanism of the fuel cell materials in situ. However, Raman spectroscopy is now increasingly being used to map intricate chemical reaction mechanisms at the anode. Art objects are spectroscopically examined to reveal their age, composition, and to optimize conditions for conservation. The non-destructive nature of Raman microspectroscopy makes it well suited for this purpose. By focusing a laser on the art sample and plotting the intensity of inelastically scattered light, spectra of artists' pigments, binding media, or varnishes can be obtained. Raman spectroscopy is even used to identify falsification of artworks. You've just watched Joe's introduction to Raman spectroscopy for chemical analysis. You should now understand the principles behind the Raman effect and how it applies to Raman spectroscopy, how to perform your own Raman analysis in the lab, and some of the exciting ways in which it's being applied in industries today. Thanks for watching.